So the second paper is about autogenous shrinkage in a high-performance concrete with chemical admixtures. And I think it's Annette Godul-Polanco will present this paper from the Facultad de Ingeniería Civil in Monterrey, Mexico.
Thank you. Good afternoon. My name is Jennifer Canol, and this is a part of my master thesis. I'm currently a master student degree in Universidad Autónoma de Nuevo León. Durability in high-performance concrete have resulted in the development of chemical and mineral admixtures to mitigate several concrete deterioration. Of course, high-performance concrete has high amounts of cement and supplementary cementitious material, and it has water-cement ratio below of the 0.4. But even if we have this amount of cement, we cannot ensure that the durability is going to be higher, because we are going to have cracking potential. So if we want to mitigate the chloride penetration of the concrete, we have to take in account the phenomena that cause the cracking potential, like dry and shrinkage, that is due to the evaporation of the loss of the water inside the concrete. And we have the worst, that is autogenous shrinkage, that appears in the early age of the concrete. So this is the major problem, because you are going to have cracks at the first day maybe, or the 2 day, and then even if you have high amounts of cement, you are going to have cracks, and then chloride can penetrate in that side. So against the chloride is commonly used the corrosion inhibitor admixtures based on calcium nitrate. There are like 20 years that has been used these chemical admixtures. Against dry and shrinkage, you can use shrinkage reduction admixtures, and against autogenous shrinkage, you can use also the shrinkage reducing admixtures. It depends on the chemistry of this kind of admixtures, and also you can use internal curing with lightweight aggregates or superabsorbent polymers. And also you can use silica fume to densify your concrete, but the silica fume is going to increase the autogenous shrinkage. So you have to take in account when you use silica fume, because it's a difficult material to use, but it's a good one if you know how to use it. So if in this project we use the corrosion inhibitor admixture, and also we use shrinkage reducing admixtures, and also we use the internal curing, and you will say it's going to be a good concrete, but you don't know the performance of the corrosion inhibitor admixture in autogenous shrinkage, because it has another use. But if you don't know how this admixture is going to be in the autogenous shrinkage, you probably are going to do something wrong. So we use all these admixtures, and we measure the autogenous shrinkage in the concrete. What about autogenous shrinkage? Well, it's the linear deformation of the concrete due to the hydration of the cementitious materials, and this is measured in sealed condition and controlled temperature. So it's not the same. You are not going to lose water, so you have to take in account when you measure the autogenous shrinkage. And also there is a difference between chemical shrinkage and autogenous shrinkage, because chemical shrinkage is the total volume of the concrete shrinks, and the autogenous shrinkage is just the linear deformation. It don't take into account the voids inside the paste. So the better way to measure autogenous shrinkage is with the ASTM C1698. So in this project, we use 1% of shrinkage reducing admixtures, 2% of calcium nitrate. We use superabsorbent polymers with internal curing water. This is a kind of new material that is used in the high-end industry and currently in the concrete industry. And also we use silica fume, because if you talk about high-performance concrete, you have to have some pozzolan inside of your concrete, and we decided that silica fume is the commonly used in Mexico at least, and a water cement ratio of 0.4. So if you are going to use all this admixture, you have to choose a good model to design your mortars. In this case, we choose to use the Powers model with the modification of Professor Jensen, who changed the Powers model to use cement and silica fume in your system. The main objective is evaluate the autogenous shrinkage in Portland cement silica fume high-performance concrete with the chemical admixtures. And the specific is to establish the addition of silica fume to consume all calcium hydroxide through thermogrammetric analysis. So we are not going to put some different addition of silica fume, just one, but that one has to consume all calcium hydroxide, at least in the theoretical way. Determine the assessment of the internal curing technique to mitigate autogenous shrinkage in the Portland cement silica fume mortars with the chemical admixtures. We have to know if the chemical admixture is going to influence the autogenous shrinkage in a bad or in a good way. And also, other objective is to design the Portland cement silica fume through the Powers model with a hydration degree of 1. I'm going to explain this later. The materials are an OPC, or ordinary type 5. It means that with low content of C3A, silica fume in dry powder, crushed limestone fine aggregates from Monterrey, Mexico, and the SAP that I use is a polyacrylamide potassium polyacrylate with absorption of 25 grams per gram of water and a desorption of 90% in pore solution extracted from pastes of cement and silica fume. And a superplasticizer. The corrosion inhibitor admixture is based on calcium nitrate in a shrinkage reduction admixture. In the experimental details, we can have the calculation of the silica fume. We have to do this with thermogrammetric analysis in 7 pastes of water cement of 0.4 and also with silica fume and with calcium hydroxide pastes, because you have to know how much is going to consume the silica fume in a rich environment of calcium hydroxide, but also you have to know how much calcium hydroxide is going to produce your cement, and with this value you can do you can calculate a silica cement ratio, and you can have the perfect, in a theoretical way, addition of silica fume to consume all your calcium hydroxide in your cementitious matrix. This is the equation that I use to calculate all the calcium hydroxide contents and also the silica cement ratio. In the case of the Powers model, we use this model because Powers explained that in cementitious matrix you have 3 types of water: capillary water, bounded water, and gel water. So also you are going to have the chemical shrinkage, that is the volume reduced due to the hydration of the cement with the water. But when you have silica fume, you are going to have another system, because the silica fume is going to take water from the system. So Powers say that the bounded water was 23 grams per gram of cement, and the gel water was 0.19 grams per gram of cement. So you can reach an hydration degree of 1 if you have a water cement ratio of 0.42 or more. If you have less, you are going to have unhydrated cement in your system. So that amount of cement is going to use like filler, not like a cementitious material. So with internal curing water, you can add that water that needs the cement after the hardening or after the setting time. So with the modification of Jensen, you can know the amount of water that you need, that need the cement and also the silica fume. So we put the internal curing water in the same volume of the chemical shrinkage, so you are not going to have the linear deformation of the autogenous shrinkage if you calculate well the absorption of the SAP, of course, and if you calculate well the chemical shrinkage of your cement and the chemical shrinkage of your silica fume with the cement. Also, you have to take in account that this model says that the rate of hydration of the cement is the same of the silica fume, and this cannot be true. So you have to take into account this thing. Also, you have to know that silica fume doesn't bound chemical water, just absorb water. Silica fume takes the bound water of the calcium hydroxide. And then you have these formulas, and when thermogravimetric analysis and the chemical shrinkage, you can calculate all these values from the Powers model, and you can know the internal curing water and also the SAP that you're going to add to your system. And the paste tests were made at 28 days, so we take in account that in 28 days or more, you are going to reach an hydration degree of 1. In the results of the TGA, we have that the cement produced 0.16 grams per gram of calcium hydroxide, and the silica fume consumed 1.7 grams per gram of calcium hydroxide. So the silica cement ratio to consume all calcium hydroxide in your system is going to be 0.095. It means a 9.5% of addition of silica fume are going to consume all your calcium hydroxide from the cement if you mix it well, of course. It has to be well distributed, because if you don't do that, the silica fume is not going to reach the calcium hydroxide. It means that this addition is in a perfect condition, of course. Then we have the results of the chemical bounded water from the TGA measurements, and as Power say, it was the same. It's what I calculate 0.23 grams per gram. And the gel water is a theoretical value, also for the silica fume. Then I calculate the chemical shrinkage, and as can you see, cement has 6.03 milliliters per set per 100 grams of material of chemical shrinkage, and the silica fume has 3 times more. So it means that you are going to have more autogenous shrinkage in your system. This is the mixture design of all of the mixtures. Of course, we have a reference without no admixtures. Then you have the reference with the SAP, then with the shrinkage reduction admixture, then you have with the calcium nitrate inhibitor, then you have the combination of all the admixtures to know the influence of all these in the autogenous shrinkage measurements. And we measure the fresh properties, and we have a target of the spread that 24 centimeters plus minus 1 centimeter. And in the results, we can see that the incorporation of the superabsorbent polymers increase the air content, and all, of course, are going to lower the unit weight of the mortars. And finally, in the results of autogenous shrinkage, we can see that the first line, that is the purple one, is the SAP with the shrinkage reducing admixtures. Both are characterized for decrease and mitigates the autogenous shrinkage. So if you have values, negative values, you have shrinkage. If you have positive values, you are going to have expansion. So what you want is 0. And it means that if you add to your system SAP and shrinkage reducing admixture, you're not going to have any shrinkage at all. It means that your potential cracking is 0. Then you have the mixture with the SAP, that is the blue one, and it has like until 28 days like 15 micrometers, that is almost nothing. So the amount of internal curing water was the correct. Also, if you see in the red one, is the one that has all the admixtures. It means that the internal curing water mitigates the effect of the other admixtures, because calcium nitrate is well known that accelerates hydration, so you are going to have more autogenous shrinkage, and also provides, they say, microcracking, but I don't corroborate this data that I look in the literature. Also, we have the other blue one below of the red one that is just the shrinkage reducing admixture, and it has a low value. But then, in the yellow one is shrinkage reducing admixture and calcium nitrate. You can see that the calcium nitrate is going to increase the autogenous shrinkage, but the shrinkage reducing admixture mitigates a little bit the influence of the calcium nitrate. And the green one is the reference, and for autogenous shrinkage values, minus 250 is a big value. So you are going to have a higher cracking potential with this autogenous shrinkage value. And finally, the brown one is the mixture with the calcium nitrate that is the worst behavior in the system. It means that if you're going to use calcium nitrate, you have to be sure that mitigate this value, because even if you want to protect your steel reinforcement, you can have cracking potential in your concrete, and maybe, I don't know, because I don't measure this, you are going to have a potential corrosion more fast than if you don't put this admixture. And for the conclusion, we have that the model to calculate the required amount of SAP and internal curing water, it means that the Powers model, has proven to be effective to mitigate autogenous shrinkage of an age of 28 days. Also, mixtures with SAP mitigate autogenous shrinkage and inhibits the effect of the chemical admixtures. We have that shrinkage reducing admixture decrease the autogenous deformation by 33%, even with the presence of the calcium nitrate. So you can use also this admixture to mitigate the bad behavior of the calcium nitrate in the autogenous shrinkage. We conclude that calcium nitrate increases the autogenous deformation by 100%, and SAP and the shrinkage reducing admixtures inhibit the effect of calcium nitrate in the autogenous deformation. And finally, chemical admixtures have an influence in the crack potential of the concrete, and they should be tested before using, because you can have cracks at early age, and you can affect the durability of your high-performance concrete, even if you have high amounts of cement and high amounts of supplementary cementitious materials. Thank you.
Thank you. We have time for one or two questions.
Thanks for the presentation, Alejandra. I would like, I was missing, which is the mechanism by which the calcium nitrate is producing the highest shrinkage? Because I couldn't understand why is the calcium nitrate producing so high shrinkage.
The calcium nitrate accelerates the setting and the rate of hydration because they release calcium ions. So this increases the rate of hydration, and this provokes a micro cracking at the beginning. That's why we expect that this happened in the results of autogenous deformation was higher than the reference.
Another question? Can you comment on the scatter of your curves or the possible sources of deviation? I mean, for example, was it at a constant control temperature? Because sometimes it may create some.
Yes, it was, because you cannot measure autogenous shrinkage without control temperature. It was according to the ASTM, everything, even the standard deviation, that I think for mortar was 28 micrometers per meter. And also you have to check the drying effect, and has to be less of 0.01%, and also we check that.
And How many specimens per?
Was 6 per mixture.
No other question? So thank you very much.
Thank
and we
you.
move to the next presentation.